Hi, I am Crystal. Welcome to Chapter 4 Elements and the Periodic Table. For ease of understanding, I have divided this chapter into 4 sections. First section is about atoms and elements. Second section describes about organizing the elements and periodic table. Third section is about metals, nonmetals, and inert gases. And the fourth section is about radioactive elements and its uses.
Hi, this is Mike. I am going to explain about the first section called atoms and elements. Basically, the atom is a basic unit of matter that consists of a dense central nucleus surrounded by a cloud of negatively charged electrons. The name atom comes from the Greek atoms, which means unbreakable. Atoms can only be observed individually using special instruments such as the scanning tunneling microscope. Over 99.94% of an atom's mass is concentrated in the nucleus, with protons and neutrons having roughly equal mass. In modern scientific usage, the atom is composed of various subatomic particles. The constituent particles of an atom are the electron, the proton, and the neutron. The electrons have a negative charge. It is the least massive of these particles at 9.111031 kilogram. Too small in size. Protons have a positive charge and a mass 1,836 times that of the electron at 1.6726 and 27 kilogram. Neutrons have no electrical charge and have a free mass of 1,839 times the mass of electrons. Now we will move to elementary particles. In the standard model of physics, both protons and neutrons are composed of elementary particles called quarks. The quark belongs to the fermion group of particles, and is one of the two basic constituents of matter, the other being the lepton, of which the electron is an example. Protons are composed of 2 up quarks and 1 down quark, while a neutron consists of 1 up quark and 2 down quarks. This distinction accounts for the difference in mass and charge between the two particles. The quarks are held together by the strong nuclear force, which is mediated by gluons. Nucleons, all the bound protons and neutrons in an atom, make up a tiny atomic nucleus and are collectively called nucleons. Within a single element, the number of neutrons may vary, determining the isotope of that element. The total number of protons and neutrons determine the nuclide. The number of neutrons relative to the protons determines the stability of the nucleus, with certain isotopes undergoing radioactive decay. The neutron and the proton are different types of fermions.
Hi, this is Kate. Now we are going to learn about the second section called Organizing the Elements and Periodic Table. About 70 elements had been found by the mid-1800s. Mendeleev was the first to organize them in a systematic way. He listed the elements in order of increasing atomic mass and arranged the elements in columns, so those with similar properties were side by side. He left blank spaces where nothing could fit. He predicted the physical properties of the missing elements. Moseley determined the atomic number of the elements and arranged the table by atomic number, instead of atomic mass. Now we will discuss about periodic table. The modern periodic table is arranged by atomic number. The periodic table has atomic number increasing from left to right and top to bottom. The horizontal rows on the periodic table are called periods. Properties change as you move across a period. There is a periodic repetition of the chemical and physical properties of the elements. This is called periodic law. Now we will see the arrangement of groups in periodic table. When the elements are arranged in order of increasing atomic number, it is observed that certain properties seem to repeat in a regular way. We start a new row, which is a period, so that elements with similar properties fall in the same column. Each vertical column is called a group or family. Let's discuss different groups in periodic table. Group 1, alkali metals or lithium family. Group 2, the alkaline earth metals or beryllium family. Group 3, the scandium family, consisting of the rare earth elements plus the actinides. Group 4, the titanium family. Group 5, the vanadium family. Group 6, the chromium family. Group 7, the manganese family. Group 8, the iron family. Group 9, the cobalt family. Group 10, the nickel family. Group 11, the coinage metals or copper family. Group 12, the zinc family. Group 13, the trials, boron group or boron family. Group 14, the tetrals, carbon group or carbon family. Group 15, the pnictogens or nitrogen family. Group 16, the chalcogens or oxygen family. Group 17, the halogens or fluorine family. Group 18, the noble gases or helium family or neon family. Different block in periodic table. Groups 1 and 2 come under S block. Electron configuration ends in an S sublevel. Groups 13 through 18 come under P block. Electron configuration ends in a P sublevel. In S and P block, highest energy level is equal to the period number of the element. D block elements comes from groups 3 to group 12. Electron configuration ends in a D sublevel. Highest energy level 1 less than the period number of the element. F block elements are called inner transition metals. Electron configuration ends in F sublevel. Highest energy level is 2 less than the period number of the element. Now we will discuss about transition and inner transition metals. The transition metals or transition elements traditionally occupy all of the D block of the periodic table. The transition metals represent the transition between group 2 of 2 elements and group 13 of 3 elements. The inner transition metals occupy the F block of the periodic table, and again act as a transition between group 2 elements and the transition metals.
Hi. I am Paul. I am going to explain about third section is about metals, non-metals, semi-metals and inert gases. First we will discuss about metals. Most elements in periodic table are metals. There are so many metals, they are divided into groups: alkali metals, alkaline earth metals, and transition metals. The transition metals can be divided into smaller groups, such as the lanthanides and actinides. Most metals are good thermal conductors and electrical conductors. In addition, some metals are magnetic. Most metals are solids at room temperature. Mercury is a liquid at room temperature. Let's discuss about alkali metals and alkaline earth metals. The alkali metals are located in group 1A, first column of the periodic table. Sodium and potassium are examples of these elements. These elements are less dense than other metals, they have ions with a +1 charge, and have the largest atom sizes of elements in their periods. The alkali metals are highly reactive. Alkaline earth metals are located in group 2A, second column of the periodic table. Calcium and magnesium are examples of alkaline earths. These metals form many compounds. They have ions with a +2 charge. Their atoms are smaller than those of the alkali metals. Now we will discuss about transition elements. The transition elements are located in groups 1b to 8b. Iron and gold are examples of transition metals. These elements are very hard, with high melting points and boiling points. The transition metals are good electrical conductors and are very malleable. They form positively charged ions. Now we will discuss about lanthanides and actinides. Lanthanides. When you look at the periodic table, you'll see there is a block of 2 rows of elements below the main body of the chart. The top row has atomic numbers following lanthanum. These elements are called the lanthanides. The lanthanides are silvery metals that tarnish easily. They are relatively soft metals, with high melting and boiling points. The lanthanides react to form many different compounds. These elements are used in lamps, magnets, lasers, and to improve the properties of other metals. Actinides. The actinides are in the row below the lanthanides. Their atomic numbers follow actinium. All of the actinides are radioactive, with positively charged ions. They are reactive metals that form compounds with most nonmetals. The actinides are used in medicines and nuclear devices. Next, we will move to nonmetals. Nonmetals have properties opposite those of the metals. The nonmetals are brittle, not malleable or ductile, poor conductors of both heat and electricity, and tend to gain electrons in chemical reactions. Some nonmetals are liquids. These elements are shown in the figure. Next, we will learn about metalloids. The metalloids, or semimetals, have properties that are somewhat of a cross between metals and non-metals. Metalloids tend to be economically important because of their unique conductivity properties, that is, they only partially conduct electricity, which make them valuable in the semiconductor and computer chip industry. The metalloids are shown in the figure. Now, we will discuss about the noble gases. The noble gases are helium, neon, argon, krypton, xenon, radon and ammonium occupy the rightmost group of the periodic table. Noble gases were also known as inert gases and rare gases. Some noble gases have been shown capable of forming compounds mainly with fluorine. Argon and helium cannot be considered rare, as argon makes up about 1% of our atmosphere and helium is the second most abundant element in the known universe. The extremely low chemical reactivity of the noble gases is due to them having a complete valence shell. They tend not to gain or lose electrons. The noble gases have high ionization energies and negligible electronegativities.
Hi, this is Crystal. I am going to explain about fourth section radioactive elements and its uses. A radioactive element is a pure chemical substance consisting of one type of atom distinguished by its atomic number. Radioactive decay is the process by which an atomic nucleus of an unstable atom loses energy by emitting ionizing particles. Usually, radioactive decay happens due to a process confined to the nucleus of the unstable atom, but, on occasion, an inner electron of the radioactive atom is also necessary to the process. Radioactive decay can produce alpha particles, beta particles, and gamma rays. These are forms of nuclear radiation. Alpha decay consists of 2 protons and 2 neutrons. It is positively charged, and same as helium nucleus. The release of an alpha particle by an atom decreases the atomic number by 2, and the mass number by 4. Some atoms are unstable, because they have too many neutrons. During beta decay, A neutron inside the nucleus of an unstable atom changes into a negatively charged beta particle and a proton. A beta particle is a fast-moving electron given off by a nucleus during radioactive decay. The new proton remains inside the nucleus. Beta particles are much faster and more penetrating than alpha particles. Beta particles pass through paper, but they are blocked by an aluminum sheet 5 mm thick. Beta particles can also travel into the human body and damage its cells. Alpha and beta decay are almost always accompanied by gamma radiation. Gamma radiation consists of high-energy waves, similar to X-rays. Gamma radiation has no charge, and does not cause a change in either the atomic mass or the atomic number. Gamma rays are the most penetrating type of radiation. You would need a piece of lead several centimeters thick, or a concrete wall about a meter thick to stop gamma rays. Gamma rays can pass right through a human body, delivering intense energy to cells and causing severe damage. Now we will see the uses of radioactive elements. In 1896, the French scientist Henri Becquerel discovered radioactive decay quite by accident, while studying mineral containing uranium. Natural radioactive decay can produce alpha particles, beta particles, and gamma rays. Uses of radioactive isotopes include tracing the steps of chemical reactions and industrial processes, and diagnosing and treating disease. Doctors use radioactive isotopes to detect medical problems and treat some diseases.
With that, we come to the end of the chapter. This narration was presented by SchoolinMobile. Please visit us on the website SchoolinMobile.com.